Welcome to our video on the implementation of a reliability-centered maintenance plan for fire tube boilers in the textile industry. In this study, we explore how to optimize maintenance programs for fire tube boilers through the application of RCM principles. By anticipating potential failures and evaluating consequences, the aim is to enhance system reliability and prevent unplanned stoppages. We used the analytical hierarchy process, AHP, to conduct a criticality analysis of the boiler equipment and evaluated failure modes and effects to calculate the risk weighting number, RWN. In our case study, AHP was utilized to prioritize systems in the boiler area. The methodology involved a criticality analysis using the analytical hierarchy process, AHP, to assess equipment in the boiler area. Failure modes and effects were evaluated, and the risk weighting number, RWN, was calculated to prioritize maintenance tasks. In the AHP methodology, the inconsistency ratio, IR, is a crucial metric that assesses the consistency of judgments made during the pairwise comparisons of criteria and sub-criteria. It helps to identify any inconsistencies in the decision-making process. The inconsistency ratio, IR, is calculated based on the consistency index, CI, and the maximum eigenvalue of the judgment matrix, providing insights into the reliability and coherence of the prioritization process. Results of the inconsistency ratio, IR, calculation are used to rank the level of importance of criteria and sub-criteria from highest to lowest. A lower inconsistency ratio indicates a more consistent and reliable decision-making process. The risk weighting number, RWN, is computed by multiplying the severity, failure frequency, and detectability indices of a specific component. This quantitative value represents the risk associated with a potential failure in that component. The proposed maintenance plan serves as a structured guide for optimizing maintenance tasks for critical components in the steam boiler system. Maintenance tasks are selected based on consequences of failure and evaluated for effectiveness using specific criteria. Maintenance intervals are assigned based on the calculated risk weighting number, RWN, for critical components, with reliability calculations performed using the Weibull distribution. The study resulted in a detailed maintenance plan for the boiler system, with optimal time intervals determined using the Weibull distribution for critical components. The study resulted in a detailed maintenance plan for the boiler system, with optimal time intervals determined using the Weibull distribution for critical components. Reliability is crucial in the operation of industrial equipment, which is why we have conducted a detailed comparison between the reliability of the current maintenance plan and the proposed plan. We used a reliability block diagram to assess the performance of the entire boiler system. By assigning codes to components and subsystems, we were able to identify areas for improvement and compare the results obtained with the implemented maintenance strategies. This comparison allowed us to clearly visualize how the new proposed plan would impact the reliability and availability of the boilers. The results of our reliability comparison revealed a significant increase in system reliability and availability. The reliability over time in the graph has the expected trend level, two negative exponentials with different slopes due to different failure frequencies. The maintenance cost due to corrective and preventive maintenance has been evaluated using the equation for all components, both for the current and proposed scenarios. This representation helps identify and highlight the most crucial components in terms of cost, as well as focus on those whose maintenance costs can be easily reduced. Therefore, the difference in maintenance costs, calculated as current maintenance cost minus proposed maintenance cost, is $26,873.44, representing average savings of 27.54%. The RCM methodology optimizes maintenance resources by analyzing the reliability of critical equipment, such as boilers, to ensure production, safety, and environmental protection. The proposed plan increases reliability by 16.15% and reduces maintenance costs by 27.54%. The methodology enhances system reliability and can be applied to other textile industry systems. Future implementation of Smart RCM, incorporating Industry 4.0 technologies, promises further improvements in performance and cost reduction, despite challenges related to workforce adaptation.